So hello everyone, welcome to OneClass. My name is Shanjida. I am currently a second year human biology student at U of T. And so today I'll be going over some commonly asked chemistry questions both at the high school / university and college levels. And if anyone needs any additional schoolwork help or needs tutoring, you can check the description box below. And other than that, let's get started. Okay, so our first question here says, is xenon is XeF4 polar or non-polar? Explain your answer. Okay, so this is xenon. F4, right? And so, okay. And so we have to first see if this structure is what this structure basically is, okay? And so let's first draw out the structure. So as you can probably guess that our central atom here would be xenon and our fluorines would be surrounding it. Okay, and so basically this is your Lewis structure, and so you can see we have 4 XeF bonds, and so what this is you can see that this is the symmetry. So this portrays basically symmetry. You can say symmetry of the dipole moments, okay? And so how you distinguish if it's polar or non-polar? So how do you distinguish? How to distinguish polar versus non-polar, right? And so this has to do with basically difference. So I'll say so basically we can say the difference of electronegativity. Electronegativity of the atoms that are involved. Okay, and so if the structure, so how do you distinguish from the structure? So basically if you have a asymmetric structure, right? So the molecule is non-polar, okay? And so because of the non-zero dipole moments present in the molecule. And so since we have 4 xenon and fluorine bonds, they will eventually cancel the dipole moments because of their planar form, right? We can see here that it's basically it's basically planar, and it has, so the bonds that are here, they are basically the same, and so they will cancel out the dipole. Okay, and so what we say here is the 4 XeF bonds will cancel the dipole because of their planar form. Okay, and so because they are positioned this way, the possible dipole moment present in the central atom will basically cancel out, right? So your central atom over here, it would cancel out. And so basically we can also say, so we can basically say here that trifluoride is a non-polar molecule. And so what I have basically, I didn't draw here are the lone pairs. So I'll just denote lone pairs here. And so xenon, you can see here it forms 4 bonds here, so it's sharing 2 electrons in each of the bonds, but however it also has 2 more lone pairs. And so fluorine would have 6, right, to get a full octet. So it would have 3 lone pairs, each of the fluorines in this case. Okay, and so basically what we have here, all of the bond dipoles you can see here would be cancelled out because of their planar form. Okay, and so you can see that the form over here is planar, they're all basically the same, and so we can say that XeF4 is a non-polar molecule. Okay, and so the solution is correct. Okay. So our next question here, question 2, says the aqueous designation listed after a solute indicates the process of hydration. Using potassium bromide and C2H5OH as your examples, so ethanol, explain the process of hydration for soluble ionic compounds and for soluble covalent bonds. So they're telling us to explain how they got how did they get potassium bromide and ethanol from hydrations basically. And so so for potassium bromide, right, as you can probably get like know by now, is that potassium is a metal, right? It's from the group 1, right? Group 1, and so this is a non-metal, and so we can probably say that this involves the concept. Sorry, this says involves. So involves the concept of soluble ionic compounds. Okay, so you can see this is an ionic compound. So basically, when soluble salt dissolve in water, the ions in the solid separate, and they basically spread across the solution, in the solution basically. And so basically you have so when a salt dissolves in water, its ions are spread throughout the solution. Okay, and so this process, right, is known as dissociation. Okay, and so let's say for example we have, we have potassium chloride. This is our salt. Okay, and so when you add water, right, so when you have water, so let's say for example reacts with water, right, and so what you basically get is the water molecule, the hydrogen, is attracted to the negative chloride ions, right? So I'll just write this KCl, right? If this is a reaction, our hydrogens are going to be basically attracted to the chloride ions. So you have basically HCl, right? And then what you have here is your potassium would react with your oxygen, and so you would basically have, right, and so in order to balance this basically, so you have to balance this equation, and to do that let's first balance this equation. So we have two hydrogens on this side, and so we have to have two hydrogens here, therefore we have 2, and so basically what you have here, HCl, okay, oops, so you have 2, and therefore you would have 2 over here, 2 over here, but since we have only 1 oxygen here, that would mean we would have 4, right? But however, so if you have, sorry, actually let's not write this equation out. We can just say that we can just say here that our potassium is attracted to our oxygens, and we can say here that our chlorides, Cl negatives, are attracted to our hydrogens here, okay, and so negative to negative right here, okay, and so what we have here is that the water molecules are surrounding the individual K plus and Cl ions, and so reducing the strong forces that bind the ions together, and so that will let them basically bind the ions together and letting them move off into the solution as basically dissociation. Okay, and so that's what it means basically. And so when we look over here, that this when the water molecules surround the individual ions, the potassium and the calcium ions, it reduces the strong forces which lets the ions bind together and move into the solutions as like individual ions, basically. Okay, and so when we have ethanol here, this involves the concept of organic compounds, right? So another example, when we have basically this is ethanol, right? And so this involves the concept of soluble organic compounds, because this is an organic compound. Okay, and so because we have carbons here and hydrogens, and so the polarity of organic molecule is actually determined by the presence of the polar bonds, right, to the electronegative atoms. In this case it would be oxygen, and the polar functional groups, right? And we have our functional group here. So our functional group here is OH, a hydroxyl group, or alcohol. And so the overall polarity balance the non-polar parts of the polar parts. And so what happens is when you have a large non-polar organic hydrocarbon, this will tend to make it less soluble, right? Because so we can say compounds that are soluble or that dissociate in water, right? They're gonna have some sort, so they're gonna have a proton. So let's say OH, OHs basically, and H2s. All your functional groups, so for example those. But if we don't, so like non-solubles would be like large hydrocarbons, and so these are basically your large carbon chains. Okay, these are basically compounds that have a lot of carbons, and so whereas when you have more polar parts, they will tend to be more water soluble. So we can say polar molecules are more water soluble because of that electronegative difference. And so non-polar are less water soluble. Okay. And this is what they have over here. So a larger non-polar organic hydrocarbon will be less soluble, and so more polar would be soluble in water, and so this is correct. Okay, so our next question here says, what mass of sodium, I think this is, okay, is required to precipitate all of the silver ions from 75 milliliters of 0.1 mole concentration of solution of silver nitrate. Okay, so first of all, let's set up a chemical equation for the reaction of these two compounds. And so this would be a double displacement, right? Because we have basically two different, you can say, compounds reacting with each other, which both involves two different compounds. And so we can write this as Na2 Cr4 plus silver nitrate. So what you have, so right, you would have Na, sorry, so we would just balance this equation. You would have 2Na NO3 plus you would have G2 Chromium, sorry, CrO4, okay? And so you would basically have a 2 over here, okay? And this balances your equation. And so this is basically an important part for solving the problem because we will be using stoichiometry. And so the problem here wants us to get the mass of sodium, of this sodium compound here, and so that is needed to precipitate the silver ions present in silver nitrate. And so this means that all the moles present in silver nitrate will be consumed, okay? So basically what we have here is, so the wants us, so required, we can say required here as mass of or needed to precipitate all the silver ions in silver nitrate, right? And so we can say, so just say, we can say that, so this means all the moles present in AgNO3 is consumed or will be consumed basically. And so when you're reacting this equation, so we can say therefore moles of the number moles of Na2NO3 is equal to number moles of silver sorry, this is supposed to be Chromium nitrate, right? Okay. And so we're given the volume here as 75 milliliters, but we have to convert this into liters, since our concentration is always moles per liters basically. And so our first step here, our first step here is to find the moles of silver nitrate, okay? So number one, find moles of silver nitrate. Okay, and so to do that, we are given our concentration and our volume, and if you recall that our concentration is equal to our number of moles over volume, right? And so we can rearrange this equation to get moles, and we have C times V, right? And so here we can basically say that M of GNO3 is basically equal to the concentration, right? We're given 0.100, so 0.100 moles, the concentration molarity, times 75 milliliters times 1 liter over 8,000 milliliters, right? We have to convert the units here. And so what we get here, so if you do the math here, we basically get 0.0075 moles of AgNO3. Okay, so this is the number of moles of silver nitrate. And now, so the second step would be to find so the second step is to find number of moles of Na2 chromium. O4. Okay, and so basically the molar ratio of if you can see here, the molar ratio here is basically 1 to 2, right? As you can see from here, from our equation here. So this is basically from 1 to 2, right? The ratio. And so what we can say here is that through stoichiometry, the molar ratio of Na2 chromium to silver nitrate is 1 to 2, right? So basically what you have to do is to find the number of moles for Na2 CrO4, you basically have to do 0.0075, right, times this by 1 mole of CrO4, divide this by 2 moles of silver nitrate. Okay, and so what I get here is so what I get here is basically I get 0.00375 moles of sodium chromate. Okay, so now what we have to do, our next step, we are almost there. What we need to do is find, before we can determine the mass, of sodium chromate, we need to find the molar mass, right? So if you remember that we have our moles and we can find our molar mass but from the periodic table basically of each of the elements. But to find the mass, right, so we can say, since our molar mass, so I'm just saying molar mass is mm, is equal to mass over your number of moles, right? We can rearrange this equation to get our mass, right? So our mass is basically equal to molar mass times your moles, right? So let's first find molar mass of sodium chromate. Oops. CrO4. Okay. To do this, we can say to find the molar mass. Let's go step by step. And so let's first find the molar mass of 2 sodium atoms here, right? We have Na2, and so the molar mass of 1 sodium atom is around 23.0 grams per mole. Since we have 2, we will multiply this by 2. So we get 23 times 2, we get 46 grams per mole. Okay, and so the other, so let's just say that one. Okay, so our next step would be to find the molar mass of chromium here, and so we only have 1 mole of chromium, and so 1 mole of chromium is basically 52.0 grams per mole, and this is given in your periodic table. And so our last step, one of our last steps to find the molar mass of sodium chromate would be to find the molar mass of 4 oxygens, right? And so we can say, so the molar mass of 1 oxygen atom is around 16 grams per mole. And then if I multiply this by 4, you get 64 grams per mole. Okay, and so the last step to find the molar mass would be to add all of the numbers together. So molar mass of Na2O4. So you just basically add all this together. You have 46. You have 52 grams per mole. You have 64. Okay, and you just add all this together, and what you get here is, so if I plus 52 plus 64, get around 162. 162.0 grams per mole. Okay, and so basically your molar mass of sodium, so molar mass of sodium chromate 4 is 162.0 grams per mole. Okay, and now we can finally find the mass needed, right, for sodium chromate here. And so we can say, thus the mass needed is, so recall that to find mass, it's right, we have our equation right here, which is molar mass times the number of moles. So our molar mass, we say mass of Na2 would be 162 grams per mole. and you multiply this by the number of moles we have, and so we have 0.0037 moles, right? And so your moles get cancelled out, and you basically get 0.607 grams mass of, so you have mass of 2CrO4. Okay, this is the mass needed. So yes, this is what I have got. So this is the next question says how to convert grams to moles. Okay, so grams and moles are both units of measurement. So grams is for mass, moles is the number of mole quantity, right, found in, let's say, 12 grams of carbon is roughly 6.02 times 10 to the power 23. This is the Avogadro's number, right? So where 1 mole of any substance is exactly 6.02 times 10 to the power 23 particles. And so in converting grams to moles, there's a conversion factor here. So you have, so basically to find, we can say, so we can say to find grams in this case. So let's first address how we get this, which equation it comes from. So the equation, we can say simply here is that grams and moles are used as units for molar mass, right, which is grams per mole. And so we can basically say molar mass is equal to grams per mole, which is basically mass over moles, right, your N, right? And so so we are trying to get to find to convert to find basically moles, right? And so we can basically say that we're trying to get grams. Let's find grams first. So we are just gonna multiply molar mass times moles in this case, and this is how you find moles, mass. And so basically what you have here is so you can basically say that so you can basically say mass is equal to molar mass times the number of moles. And so you can also say to find the molar mass, you can you basically add up the individual molar masses of the element present in the substance, right? And so we can basically, let's say we want to convert 5 grams of water. Okay, so let's say, for example, we want to convert, let's say here, 5.0 grams of water, right, into moles. 2 moles. And so to do this, let's calculate the molar mass of the molar mass. So the first step would be to calculate the molar mass of water. And so to do this, let's first calculate the molar mass of 2 hydrogens. So the molar mass of 1 hydrogen atom is 1.01. Since we have 2, multiply this by 2 and you get 2.02 grams per mole. Okay, again you find 1.01 from your periodic table. And so the next step would be to find the molar mass of our 1 oxygen atom here. And so the molar mass of 1 oxygen atom is 16.0 grams per mole. So the last step will be to find the molar mass of, right, since we have done all the individual elements here, and we would just add all of this together, grams per mole plus 16.0 grams per mole. Okay, I'll just add the 16 right here. Okay, and you get 18.02 grams per mole. And so now our second step, to find moles, we would need to basically we would have to convert. So when we're converting grams to moles, we can say, so since we have mass is equal to molar mass times the number of moles, we can say moles, right, is equal to mass over your molar mass, right? And so our mass was 5 grams, and our molar mass here is 18.02 grams per mole, right? And as you can imagine, our grams will get cancelled out, and we basically get moles, we get 0.28 moles. Okay, so we can basically, therefore we can say, therefore there are 0.28 moles in 5 grams of water. Okay, so this is basically how you go from grams to moles. Okay. Yeah, this is correct. Next question. Okay, what is the molecular weight of NaOH? So we're trying to find the molar mass of sodium hydroxide here, and so molar mass sodium hydroxide. Okay, and so let's first break this down into 2 individual elements here. 3, right? We have 3 here. We have oxygen, hydrogen, and sodium. And so the molar mass of sodium, 1 mole of sodium, 1 atom of sodium is basically 23 grams per mole, right, if you round the number. And so oxygen is 16. And hydrogen is 1.01 grams per mole. Okay, and our last step would be to add this all up, right? We have, so let's say 23 grams per mole plus 16 per mole, and you have 1.01 grams per mole. If you add this all up, 23 plus 16, you basically get 40.01 grams per mole. So you can say, therefore, the molecular weight of sodium hydroxide is 40.01 grams per mole. Okay, so yeah, this is what they have got. The solution is okay. And so our next question here says, okay, so we have 12 grams of acetic acid. The molar mass is given 60 grams per mole, are dissolved in 188 grams of water, and the density of the whole solution is 1.12 grams per milliliters. Okay, and so A says, what is the weight to weight percentage concentration of the solution? Okay, so we are given here, we are given mass of acetic acid, C2H3O2, which is 12 grams. The molar mass of acetic acid is 60 grams per mole, right? Dissolved in, okay, and then we're given the mass of water, which is 188 grams, okay? And so density is also given, which is 1.12 grams per milliliters. Okay, and so let's find A first. What is the weight to weight percentage concentration of the solution? And so the formula used to determine the weight to weight percentage, so we can say weight to weight is basically your mass of solute over the mass of solution. Solute over mass of solution. And you basically multiply this by 100. Okay, I'll just multiply the whole thing by 100. And what I mean by this is, so we basically, our solute here is acetic acid is being dissolved in water, right? And so what we do here is basically say that, so we have 12 grams of acetic acid, and our solution, which is acetic acid and water, and so our total, so we need the total mass in this case, and so that would be basically 188 plus 12, okay, grams basically. And so we have here 12 grams, right? 188 plus 12 is basically 200 grams, and you multiply this whole thing by 100. And what we have here is we basically get, so we get 0.06, and you multiply this by 100, and you get 6%. Okay, so you basically have, so your weight to weight percentage is 6%. Okay. And so B says, what is the molarity of the solution? Okay, so the molarity is the ratio between the number of moles and divided by the, it's divided by the ratio of moles to volume basically in liters. And so we are given density, right? We're given density, so we can basically find our volume in this case. So to find the volume of the whole solution, we can say, so density is basically equal to mass over volume, right? And so your volume therefore would equal to mass over density. Okay, so we're trying to find volume here in order to get molarity. And so we can say the mass, our total mass of our whole solution as we calculated is 200 grams, and our density here is given 1.12 grams per milliliter, right? And so we can see, we can just cancel out the grams here and you get, so 200 divided by 1.12 is around so it's 178.6 milliliters, right? But molarity is in the volume is in liters, so we have to convert 178.6 milliliters to liters. To do that, this is our conversion factor, 78.6 milliliters. Wait, let's convert 1 liter over 8,000 milliliters. Okay, and so milliliters got cancelled. We basically have 0.1786 liters. So this is our actual volume. Oops. Okay. And so now what we have to do is compute basically for molarity. Okay. Or so what would I would do here is since we're given our grams, our mass for acetic acid and the molar mass, we can basically calculate the number of moles, and so we can say that basically we can say that number of our moles is basically, or so to how we get moles, we can, so recall that this equation, molar mass is equal to grams per mole, and so moles is basically, right, or it's equal to mass over moles basically, and so our moles is equal to mass over molar mass, and we're given the two for acetic acid. So let's calculate the moles, and so we have 12 grams. We have our molar mass of 60 grams per mole, and so if we were to do it, we would have 0.2 moles. This is for acetic acid basically. And so what we can do here, so I'll just say acidic, so basically when we have a solution here, I'll just mention when we have a solution, the number of moles of our basically what our solute is will equal to the number of moles of our solution. And so basically you can say the number of moles of acetic acid is equal to the number of moles of the solution. Okay, and so H2H3O2. Okay, so we can also say the moles of acetic acid is equal to the number of moles of the solution. Okay, and so we can use this to find molarity. Okay, and so molarity, right, which is basically concentration, is equal to N over V. So we have 0.2 over 0.1786 0.86 liters. Yes. And we basically get 1.12 molarity or concentration of the solution. Okay. And so the last question says, what is the molality of the solution? And so the molality is basically the ratio between the number of moles with the mass of the solvent in kilograms over by mass of the solution, basically, of the solvent. So the number of moles of the solute over the number of, so the mass of the solvent or the solution. Okay, so we can say molality is also denoted as small m. We can say moles over kilograms. Okay, and so we can say here, since our total mass over here, so we have calculated, is 200 grams, right? We can convert this into kilograms, and so we have 200 grams. Oops. Okay. 200 grams times 1 kilogram over 1,000 grams, and so our mass is basically 0.2 kilograms. Now we can find molality, right? Our moles is 0.2. Our moles, this is kilograms, and so the answer is, the molality is basically 1 m. Okay, and so this is your answer. The solution, the molality of the solution is basically 1. Yeah, it's basically 1. Okay, so you can see you got 6, and we have got 1.12, and lastly we have got 1 m. So the solution is correct. And so that was the end of our session. If you really like this Q&A, please subscribe, comment, like, share this video and our other videos. And if you have any personal questions or queries, you can follow the links in the description box and ask your questions. Other than that, we have went through the commonly asked chemistry questions both at the high school / university and college levels. And I'm Shanjida, and I'll hope to see